Hello. Let's start by gradient descent. And the idea is, as I said last time, that basically our functions will be C1 functions. So all of them, they have partial derivatives, and the partial derivatives are continuous functions. And here we focus on some point x tilde, and we can compute the gradient vector at at that point. And then suppose that there exists some vector such that basically the gradient vector, dot product of the gradient vector with u is negative. Okay, so let's see, why are we interested in such basically direction vector u? Let's do the Taylor expansion. So f of x tilde plus tu, so t is a positive parameter, and u is this vector satisfying this inequality. F of x tilde plus tu is f of x tilde plus tu, and basically its dot product or inner product with the gradient vector evaluated at x tilde plus lambda tu, where lambda is a number between 0 and 1. Then we basically add and subtract. So again, the annoying thing in the Taylor expansion, if you insist here on using an equality, so we want to be rigorous here, not an approximation or anything. We want to be as exact as possible. And so the idea is that if you have here x tilde, here you have x tilde plus tu, and here you have x tilde plus lambda tu. For some lambda between 0 and 1, but we have this condition at x tilde itself, and so what we'll try to do is basically to add this term and subtract it. Okay, and then this is an inner product multiplied by t. It's a real quantity, so it is definitely less than or equal to the magnitude or the absolute value. And then we have an inner product here, so by the Cauchy-Schwarz inequality, this is upper bounded by the L2 norm of this difference between the gradient at x tilde and x tilde plus lambda tu and the L2 norm of u. Okay, so if you wonder why C1 functions, so this is a place where where we can exploit the fact that the partial derivatives are continuous. So if you think about this L2 norm, it is the square root, right? And it is a summation, it's an L2 norm, so it is summation j from 1 to the dimensionality, which is n. And then we have basically the difference between the partial derivative, right? The partial derivative. Okay, so let's assume that this is xj and minus, and here xj, and so this is evaluated at x tilde plus lambda tu, and the other one at x tilde, and so we have like the squares of those differences. So because the partial derivatives are assumed to be continuous functions, then by definition, if we compare here, if we choose t to be small enough, okay, by the very definition of continuity, then basically the difference here will be small. Okay, so we can force this difference to be as small as we wish by choosing t to be small enough. And so because the partial derivatives are continuous functions, we are able actually to make this L2 norm as small as we wish. Okay, so we can make it smaller than this quantity, okay, which is minus, so this guy, this is our starting point. This guy is strictly negative. Okay, and so we can make the L2 norm less than or equal to the negative of this quantity, which will be strictly positive, divided by 2 multiplied by the L2 norm of u. Again, because by continuity, we can make this thing less than or equal to any arbitrary positive epsilon. So I can choose epsilon to be minus this inner product, which is negative, and so its minus is positive, divided by this positive quantity. Okay, and then you insert this in this expression here. So we have f of x tilde plus tu is less than or equal to f of x tilde. I mean, now you design basically this guy, Okay, so let's put it in another color. So this guy now is designed to be less than or equal to minus 1 over 2, the L2 norm, and then basically the inner product. Okay, by design, and then you multiply here, so you have this guy multiplied by the L2 norm of 2 in the denominator, and so together, and there is a t here, so the overall term, okay, so the overall term here is less than or equal to minus 1/2 t, and then this negative quantity. And then you can combine this with that, so t minus half t, this will give you half t, and you end up with this. Okay, again, t is positive, so this guy is greater than 0, and again, by assumption, this is our starting point, we are assuming that at x tilde, you can find a direction vector u, some vector u, such that the inner product of that vector and the gradient evaluated at x tilde is negative, and so this is strictly negative. So basically, this term here is negative, and so f of x tilde plus tu is strictly less than f of x tilde. What is the meaning of this exercise? It means that if you are at a specific point x tilde, if it happens that there is a vector u such that this is satisfied, this inequality is satisfied, it means that you can move in the direction of u starting from x tilde with a small enough step to reach a point which is x tilde plus tu, at which the function f is strictly less than f of x tilde. Okay, so here is f of x tilde, okay, and then there is a direction u, and you move x tilde plus tu. So if this is negative, if this inequality is satisfied, then there is a t small enough such that you can move to x tilde plus tu. Now, if you evaluate the function at x tilde, you get f of x tilde. If you evaluate the function at this point, you get f of x tilde plus tu. And according to our derivation, we have basically this is less than that. So you go to a point in the n-dimensional space where the function is lower than at x tilde, our starting point. So this seems to be like a very useful idea if you want like to do optimization, because suppose that you are minimizing a function, okay, and suppose that this function is a C1 function. So now if you initialize, you start at some point in the n-dimensional space, and then if at that point you can find the vector u, then what you can do is that you can move in the direction of u with a small enough step, and then you will reach a new point in the n-dimensional space at which the function is lower than at x tilde, and then you keep iterating, okay, hopefully to reach, perhaps a local minimum for that function. Okay, so numerical optimization is based a lot on this idea. So if we talk about machine learning basically is a bunch of optimization problems that you solve to train a network or something like this, a neural network. So optimization is at the heart of machine learning, and we solve optimization problems, but they are very difficult, and typically you solve them numerically, and the way to go is gradient descent, or at least it's a basic idea. So so this is basically the philosophy behind gradient descent. Now if the gradient at x tilde is not 0, if you choose u to be minus the gradient, this is guaranteed to give you a negative inner product between the gradient vector and u. Okay, but our above argument, it just requires this. Okay, So basically we want, okay, so we want the inner product. So we want basically the angle between the gradient vector and u to be obtuse, okay, or 180 degrees. Okay, so you don't really need to move in the direction opposite to the gradient. So again, if the gradient vector is non-zero, then one direction you are guaranteed to basically, if you move in that direction with a very small step, you are guaranteed to get a smaller value of the function is minus the gradient. So you move opposite to the direction of the gradient, but our proof above tells you you just need the inner product to be negative, which, like, if you want to think of it geometrically, if this is the direction of the gradient, you need to move in some other direction like this. Okay, so there are some algorithms in which, like, you do not insist like in moving exactly in the direction opposite to the gradient. We also learned something from this derivation above, which is a necessary condition for optimality, for local optimality, if you are solving an unconstrained optimization problem, is that the gradient at the point is exactly equal to the all zero vector. Why is this the case? Because if the gradient is not the all zero vector, then moving in a direction opposite to the gradient, if your function is C1, will lead you to a new point in which the function is strictly less than the function at x tilde. So if you want x tilde to be an optimal point, then you need the gradient vector evaluated at x tilde to be the all zero vector. So we already know this from previous lives, that basically a necessary condition for a local minimum or local optimal, generally speaking. Here we focus about minimizing function, as a matter of convention, but we can also maximize function. For unconstrained optimization, we require the gradient vector to be the all zero vector. Okay, now we define a very important set called the cone of descent directions. So basically, this is a cone. So cone is a set. It's a type of a set that, so S is a cone. What does it mean that S is a cone? So if let's say gamma belongs to S, then alpha gamma belongs to S, where alpha is greater than or equal to 0. That's the mean of a cone. The most famous cone, or I know this is an exaggeration. So one of the most famous cones is the cone of positive semi-definite matrices, right? Because you can think of positive semi-definite matrices as a set, right? And if you take any matrix that is positive semi-definite and you multiply it by a positive number, you still get a positive semi-definite matrix. Okay, so it's a cone. So a cone, again, is a name given to sets that satisfy this, that you basically scale by a positive real number, and you still get you are still in the set. So we have the cone of descent directions. Basically, these are all directions or all vectors in the n-dimensional space, such that the inner product of those directions and the gradient vector computed at x tilde gives you a negative value. Again, what is the significance of this cone? This cone, if it's non-empty, it means that there exists basically at least one direction in which, if you move in with a sufficiently small step, you will go to a point in the n-dimensional space with a value of the function f that is strictly smaller than f of x tilde. Okay, so keep this cone in mind. Now, gradient descent, again, is inspired by the above, and the idea is that you do things iteratively. You start from some point, and then you apply this step. You basically, so you start at a point, and then at the kth iteration, xk plus 1 is what? So it is the old point, and then you move in the direction opposite to the gradient. So basically, you can take step. The step can depend on k, but here in the analysis below, I will just take it to be constant. But generally, you can make it a function of k, and then you move in it. So that's minus sign. It means that you are moving opposite to the gradient. Okay. And the step size should be strictly positive. If the step size is 0, then you are stuck in a certain point. Okay. Now, of course, when you hear something like this, okay, so the intuition behind using gradient descent seems sort of valid. Okay, you move in a direction opposite to the gradient and you get a lower value of the function. But what is a guarantee that if we repeat basically this step, we will reach some local minimum? Okay, so you need actually more assumptions regarding the function, and now I will give you like a classical proof of the convergence of the gradient descent algorithm, and perhaps you already know it from other courses. So we want our function to be basically, or specifically, we want the gradient of the function to be Lipschitz continuous. Okay, so Lipschitz continuity means this inequality right here, which means that for every x and y in the space, the L2 norm of the difference between the gradient vector at x and the gradient vector at y is less than or equal to basically the L2 norm of x minus y multiplied by some finite positive constant L. So if you can find this L for the gradient of a function f, we say that the function has a gradient that is Lipschitz continuous. In homework 4, you will prove that for functions whose gradient is Lipschitz continuous, you can show the following inequality, that f of x is less than or equal to f of y for every x. So this is true for every x and y. In Rn, f of x is less than or equal to f of y plus the inner product of the gradient at y and x minus y plus this term here, which is L over 2 multiplied by the L2 norm squared of x minus y. Okay, so again, you will find a hint actually in the problem telling you how to go from the definition of the gradient being Lipschitz continuous to basically prove this statement here, which is like very important in the analysis of the convergence of gradient descent. Okay, so what we'll do is that basically under our assumption, we will apply this property here to our function, and for x we use basically the iteration x that you get in iteration k plus 1, and for y we use x that you use in iteration k. So we just use this expression here, write it down in terms of x superscript k and x superscript. So again, the superscript here is basically an index for the iterations you are engaging in while carrying out the gradient descent algorithm. Then the difference between these two vectors, by definition, I mean this is actually how gradient descent operates, right? So the difference between these two vectors is minus eta, the gradient vector, because you move in a direction that is opposite to the direction of the gradient, and you move with a small step eta. Okay, and shortly I will say how small is small. Okay, so eta must definitely be positive, else you are stuck in your place. But it turns out that like for if your function is Lipschitz, if your function has a gradient vector that is Lipschitz continuous, you need eta to be to guarantee convergence and so on, you need eta to be 1 over n. So a small step like here will be 1 over n. So here there is like an assumption that that you know L, you know the parameter L of the function, and if you don't know it, then books on optimization will tell you actually how sort of to estimate it or to have a feeling of what L should be, and hence what eta should be. But again, this is outside the scope of this course. Okay, so you rewrite this difference in terms of the gradient, you combine the terms, and then you get this nice inequality that f of x of k plus 1 is less than or equal to f of x of k, and then this quantity here that involves the step size. So this eta that you use, it has several names. So typically the optimization guys will call it step size. in the context of adaptive filters and neural networks and so on, some people call it the learning parameter. Okay, so it may appear like with different names, but it is actually the step that you take while carrying out gradient descent. Okay, so we will take eta to be upper bounded by 1 over L, and from that you can basically upper bound this term here by eta over 2. Okay, so you can use basically this inequality to show that f of x k plus 1 is less than or equal to f of x k minus eta, and then the L2 norm squared of the gradient at x, like this. Okay, and then what you do is that you subtract from both sides the optimal value, so minus f of x star. So f of x star is the minimum. Okay, so minus f of x star minus f of x star. Okay, so x star is basically the point at which the function is minimum. Okay, and so here it is. So f of x star is the minimum and x star is the minimizer. Okay, so we can subtract it from both sides, and now we get something that is very good news now. Okay, if you carry out gradient descent and your function has gradient vectors that are Lipschitz continuous, and if you basically stick to a step size that is strictly positive but less than 1 over L, then the difference between the function at the k plus 1 iterate minus, so the true minimum is upper bounded by the difference between the true minimum and the function at the kth iteration. Okay, so here evaluated at x of k minus something. And so if the gradient, if this gradient is not 0, then this term here is strictly negative. And so how can we interpret this inequality? It means that you are always like sort of getting closer to the optimal value, the minimum of the function, which here is f of x star. Okay, so this is good news, which means that in each step, so basically carrying out your algorithm under our assumption, it will not happen, to put it this way, it will not happen that you move away from the minimum value of the function. It's always the case that this difference here is upper bounded by this difference. Again, note that this is at iteration k, this is k plus 1, and then you have basically a negative quantity here, unless the gradient vector is exactly equal to 0. So this sequence is non-increasing. So that's good news. But again, typically we are interested in like something more. I mean, so will there be convergence, and what is the speed of convergence? The part above here does not require convexity. So basically, you just need the gradient vector, to be Lipschitz continuous. But now let's basically assume also that our function is a convex function. Okay. So why is this good? Because now we can have further steps of upper bounding. We can also upper bound this guy. So let's remind ourselves by a property of convex functions. So suppose that alpha and beta are in the domain of a convex function, then f of alpha is greater than or equal to f of beta plus the gradient at beta, okay, multiplied by alpha minus beta. Okay, so this is a property of convex functions that of course are once differentiable. And so we will basically apply this property for convex functions using, so alpha here is x star, which is the point at which the function is minimum, and beta is x of t. Okay, and so what you can do is that you can write down this inequality, and you can move this to the other side, and move this gradient to the other side. In other words, I mean, the idea is to upper bound this upper bound, this guy, okay? And then you can rewrite, the gradient vector. Again, since we are doing gradient descent, so the gradient vector is given by this. I mean, this is actually the iteration of the gradient descent. And you can write down xk plus 1 minus xk in this way here by subtracting, so subtracting and adding x star. And we write it like this because, like, we want like to reference everything to the optimal, right? So we take the function at the kth iteration minus, minus like the minimum, the minimum of f, and we take the value of the x vector at the kth iteration or the k plus 1 iteration, and we want basically how it is far from x star, which is basically, f of x star is the minimum value. And so again, using the property of convexity, we can upper bound this term and get, and basically get this inequality. Okay. Again, it requires that you expand. Okay, so to go from this step to that step, just simple algebraic steps. Simply, you have an inner product here. You have here the L2 norm squared of the difference between two vectors. Just expand this L2 norm squared, and you will get this result here. So this is an equality. Okay, so here we are not doing any further upper bounding. We are just simplifying the expression by expanding this L2 norm squared. Okay. Then what? Remember that basically this sequence is a non-increasing sequence. This is a non-increasing sequence. And so because it's a non-increasing sequence, then evaluating this at n, f of x n minus f of x star, okay, so you have a sequence that is non-increasing. So basically the last element, the last value is less than or equal to basically the sum of those guys divided by n, which is like the average, right? So if you have a sequence that is decreasing, then the last value is less than or equal to the average. Okay, and why is this? Why are we doing this? So basically the trick in the proof here is that in this step, if you focus on this step, you'll find something. You find a term here and a term there with a minus sign between them, and here we have k and here we have k plus 1. So basically, if you sum this quantity over k, we have a telescopic sum. Okay, so that's exactly what is like me. So why basically use this step? So this step again, why move from basically the value of this function at n, which is the last guy, and like sum here from 0 to n minus 1. So the trick is we have here an upper bound on this quantity that that is screaming, sum me, so that you get a telescopic sum and you get a simplified result. Okay, so this is a telescopic sum. Because once you put k equals 0, so this will be x of 0, x of 1. But then the next term will be k equals 1. So you will have x of 1 with the positive sign and then minus something involving x of 2. But then when k is 2, you will get plus something involving x of 2 minus something involving x of 3. So basically it's written here, okay, it's telescopic, and you end up with just two terms. So the very first term when you put k equals 0, and the very last term when you put k plus 1, when you put k equals n minus 1, and here we have k plus 1, it becomes n. And so we get that f of xn minus f of x star, that this is less than or equal to 1 over 2 eta n, and then you get this guy minus something positive, so you can upper bound again, and you just say, okay, I will just take this is 0, when you do, and then you just say, okay, I will use this as my upper bound. And now we get our equation here, which is very useful. Okay, so f of x of f minus f of x star. Okay, so what is this quantity? So this is the difference between the value of the function you get at the nth iteration, difference between the value of the function and the minimum, f of x star. We say that basically this quantity is upper bounded by the L to norm squared of the distance between your initial point, your very initial, point for gradient descent minus x star, which is basically the point in the n-dimensional space at which f of x is minimum, divided by 2 eta n. Okay, so this is basically the idea. So this upper bound, it decays as 1 over n. So decays as 1 over n. Okay, which means that if you do enough iteration, enough iterations, basically this upper bound will get smaller and smaller and smaller and smaller. So you basically crush this thing to 0. You approach f of x star. So we do have convergence. Not only we do have convergence, actually we can talk about the rate of convergence. So basically, the difference between the value of the function at the nth iteration and the value of the optimal, the minimum value, this difference is upper bounded by something that decays as 1 over n. And this is a very important result. Note the assumptions. So basically, for gradient descent to have this non-increasing sequence, we need the gradient to be Lipschitz continuous, but then to continue the proof, we need the function f also to be a convex function. In that case, you will get this here. So under our assumptions, can we do better? Using first order methods. So note that what I am talking about is an optimization technique that does not use something like the Hessian matrix. We do not go to second order partial derivatives. We just focus on the first order partial derivatives. Okay, so this is the first order technique. So if we just stick to first order techniques, can we do something better than this decay by 1 over n? Yes, we can have decay by 1 over n squared. If we use something called accelerated gradient descent, Nesterov accelerated gradient descent, and this is a brilliant idea that shows that in principle we can have gradient descent in which basically we can have decay as 1 over n squared. And there is a price. Okay, so basically in each step now we will have to do two things, and when we compute the gradient vector, we do not compute the gradient vector at the previous point. Okay, so what I will do is basically leave for you a couple of pages on Blackboard, including actually the full proof of why actually we have this convergence in accelerated gradient descent. So basically, accelerated gradient descent, it comes with like a number of flavors. On Blackboard, you will find the notes, like basically focusing on just one version that is sort of representative of the others. So it is not like trivial or it's not hiding anything, and you can show the proof. It's very, very nice. Okay. But again, it's not a course on optimization, so I will leave it to you, and perhaps you will study it in some other course, perhaps numerical optimization course. But it is nice to know that it is 1 over n squared, and to know that actually this you cannot beat 1 over n squared. You can. This is not in my notes, but in optimization textbooks, you find basically that there is another proof that you can find C1 functions. That there is no way you can carry out gradient descent on them and get convergence that is faster than 1 over n squared. Okay, any questions? So gradient descent is very important. The first few lines, telling you the philosophy of gradient descent, why it works, is are very important. And this proof of convergence is like sort of a classical that you must know. Okay. Now let's go to the KKT conditions. Here's our optimization problem. Minimize f of x. We have a bunch of equality constraints, all of them in the form of a C1 function that is equal to 0, and we have a bunch of inequality constraints, all of them C1 function that is less than or equal to 0. So this will be our standard optimization problem. Remember from the previous slide that at the point x tilde we have something called CDD, the cone of descent directions. These are the directions in the n-dimensional space that basically make an inner product with the gradient at x tilde that is strictly negative. The significance, the meaning of this cone is basically the set of directions along which, if you move a small step, a sufficiently small step, you are guaranteed to reduce the value of the function relative to f of x tilde. Now our problem is a bit complicated. It's constrained optimization problem. It's constrained. And so it's not just that we want the minimum of f of x. We want to basically we want basically to obey those constraints. Okay? So whenever you have a constrained optimization problem, like for example, the gradient at the optimal point now does not need to be equal to 0. So let me give you a trivial example. Suppose that you minimize x squared. Well, it is x equals 0. Now, suppose that you minimize x squared subject to, so st here, st is subject to x greater than or equal to 5. Okay. So here is our curve, and what is the optimal point? What is it's at x equals 5 exactly, right? Because now we want x to be greater or equal to 5. So we are focusing on this part, and on this part, the curve is going like this, and the minimum value is at 5. But is the tangent to the curve here equal to 0? No. So basically, f of x or f prime of x at x equals 5 is not 0, right? So from the very beginning, I'm telling you that basically when you have a constrained optimization problem, this idea of differentiating a function, equating the partial derivatives to 0, if you have constrained optimization problem, things are complicated, and you may get the optimal solution at the point in which the first derivative of the function itself is not 0. Okay. Now, suppose that x tilde is a feasible point. Okay. Now, we want to know the directions in the n-dimensional space along which, if we move with a sufficiently small step, we remain in the feasible set. So we remain in the points in the n-dimensional space in which basically all these constraints, we will focus on one of them, but we want the constraints to be satisfied. Right? Again, because we need now to, you cannot say that the optimal solution to this problem is x equals 0, because x equal 0 is not feasible. 0 is not greater than or equal to 5. You need a feasible solution, a value, basically an x vector that satisfies all the constraints of the problem. Okay, so we will show here something that will be like an important idea in solving this optimization problem, which is I will show that if there is a direction such that the inner product of that u, and the gradient at x tilde, if this inner product is not 0, then that direction is not a feasible direction, which means that if this is true, if you don't have a zero, then if you move along direction u, even with a very, very, very tiny step, you will violate the constraint that the function is equal to 0. Okay, so let's show this. And we show it by basically contradiction. So the gradient is not equal to 0. It may be positive, it may be negative. So suppose that there is a direction u such that this inner product is strictly negative. Okay? Then g of x tilde plus tu, again Taylor, is g of x tilde plus this term here. Then like on the previous slide, we add and subtract this term, and then Cauchy-Schwarz again, and then you say, well, we have here the difference between the partial derivatives, and since every function you see here is assumed to have continuous partial derivatives, then this L2 norm can be made as small as we wish. And so again, it can be smaller than this quantity, which is positive because this is assumed to be negative. And so you upper bound this by this term here, which is negative. So I think I missed the u. So the inner product is negative, and you multiply by t, which is positive, so you get something that is negative. So basically, if this inequality is true, g of x tilde plus tu is strictly negative. But the g functions, we want them to be 0. That's, this is basically how the constraint is structured. So basically, this means that x tilde plus tu is not feasible. And hence, it's not relevant to our optimization problem, right? Again, a constrained optimization problem, you must obey all the constraints. Okay? Now, suppose that the inner product is positive. Same thing. You start with Taylor. You add and subtract this term. Now, you use Cauchy-Schwarz, but now you lower bound by basically lower bounding the inner product by minus the product of the L2 norms. And again, because those functions, they have, those gradients or partial derivatives, they are continuous, so we can make this thing as small as we wish. And we can use this to show that if this is true, at this point the function is strictly positive. So again, x tilde plus tu is not feasible. So what is our conclusion? Our conclusion is that if is not 0, is infeasible. Again, the meaning here is that x tilde plus any small quantity multiplied by u will not be feasible. It violates the constraint. Okay. Now we have inequality constraints also. So equality constraints, we want this function to be 0. So for basically an x that is relevant to our problem, we want the function at x to be equal to 0. For inequality constraints, we just want the function to be less than or equal to 0. So inequality constraints, well, if hj of x is strictly negative, then it's okay. If it's 0, it's okay, because here we want less than or equal to 0. Suppose that the function is strictly negative. So it means that the inequality constraint is satisfied with a strict inequality. In that case, starting from the point x tilde, you can move in any direction with a sufficiently small step and still remain in the region of feasibility. Okay, so why is this true? Suppose that you move in the direction u with a step t. What is the difference between hj of x tilde plus tu minus hj of x tilde? Note that the functions we are talking about, they have partial derivatives, and the partial derivatives are continuous, so the functions themselves are continuous. And so this is upper bounded by the absolute value, which, because of continuity, this can be made as small as we wish. We can make this difference here less than any positive quantity of our choice. And because this is negative hj of x tilde, I can choose to make this distance here less than minus hj x tilde over 2. Okay, so move this to the other side, and what we get is that hj of x tilde plus tu is less than half hj of x tilde, which is negative. So, so we have hj of x tilde plus tu is negative, so x tilde plus tu is feasible for every u and sufficiently small t. So the idea is that if you are, so basically if the inequality constraint is satisfied with a strict inequality, it's like you are in the interior of the feasible set. You are inside the feasible set, and so you can, move in any direction with a sufficiently small step, and you will remain feasible. Okay? So a piece of terminology here, that if this is satisfied, we say that this constraint is inactive. So if an inequality constraint is satisfied with a strict inequality, we say that it is an inactive constraint. And now we learned something, that basically you can move in any direction and you still remain in the feasible set. Of course, this will not happen if hj x tilde is 0, because if you are exactly at the boundary, then definitely there will be directions that if you move in, you will leave the feasible set. When hj of x tilde is equal to 0, we say that we have an active inequality constraint. And like the proof I did above for the equality constraints, we can show that if there is a vector u such that the inner product is strictly positive, then this direction u is not feasible. Moving in this direction with any step, no matter how small, will get you outside the feasible set. It will make you reach a point x tilde plus tu that is not feasible. Okay, any questions? Okay, so now we define another cone, the linearizing cone. Okay, so we have the cone of, from previous pages, we have a cone of descent directions. Now we have the linearizing cone. These are the directions or the vectors in the n-dimensional space satisfying the following: the inner product between these directions and the gradient vector of any of the functions involved in the equality constraints. This inner product is exactly 0. And the inner product of D, if it's in the linearizing cone, the inner product must be if with the gradient of any function involved in an inequality constraint must be less than or equal to 0. Okay, so why basically this this cone is defined as such? So again, summary of previous results. Recall that if not equal 0, D is not a feasible direction. So here in this set, we insist that we have a 0. Also, if so, D is not a feasible direction. Also, if I didn't do the details of the proof, but it's like the proofs for the G functions, if H of K x tilde D is positive. Okay, so here what we say, okay, we are basically focusing here on directions. We are focusing on directions in which we have some hope that if we move along them, we will reach a feasible point. So basically, that's the idea of the linearizing cone. Again, if we have this or we have that, then we are sure by the previous slide that we are moving in directions that will lead outside the feasible set. We will reach some point x tilde plus tu such that no matter how small t is, we are at an infeasible point. So what we do is that we will say, okay, we will focus on directions that basically that gives you a 0 here and that gives you less than or equal to 0 there. And one important point is that those here, when we talk about the inequality constraints, we focus only on the active inequality constraints, because again, according to our previous argument, if the inequality constraint is inactive, which means that it is satisfied with a strict inequality, then it's as if you are inside, in the interior of the feasible set, and moving in any direction, so long as your step is small enough, will lead to a new point that is also in the feasible set. So here, when we involve the functions in the inequality constraints, we just focus not on the V inequality functions, we focus on B functions, at which basically, basically that are active in the sense that they are satisfied with equality constraints. Okay. Now, another cone, and this cone is difficult. Note that the linearizing cone, and this will become clear, is sometimes not very useful, but it's computationally like doable, like you can compute the gradients, right? So you can compute the gradient of the G functions and H functions. Okay, so it is sort of like, it makes computational sense if you want like a practical algorithm. Okay, then there is the cone of feasible directions. Those are the directions that if you move along them with some small step, you are guaranteed to reach a feasible set, a feasible point. Okay, so the cone of feasible directions, directions in Rn, such that there exists some t, some positive t. It can be very small, but who cares? But there exists some positive t, such that for every tau between 0 and t, x tilde plus tau d is feasible. Okay, so those are directions that if you move along them, okay, there is a value t such that if you move with a step t or less, you are guaranteed to remain inside the feasible set. what is the relationship between these two guys? In the previous, basically, when we talked previously about those g functions and h function, please be precise regarding what we proved. We proved that if this is not true, then D is not feasible direction. And if, basically, if this is true, okay, I am sorry, we showed that if this is true, if the inner product is not zero, if this is true, then D will not be feasible, in the sense that walking along it with even an infinitesimal step will not keep you inside the feasibility set. And the same thing here. Okay, so what we proved is the following, that the complement of this set, so those will be the vectors in the n-dimensional space, such that they satisfy one of these or one of those. If you move in any of those directions, you are guaranteed to get outside feasibility. And so by our previous arguments, the complement of this cone belongs to the complement of the feasible direction, the cone of feasible directions. And so basically this means that the cone of feasible directions is a subset of the linearizing cone, and later we will see an example that they are not necessarily the same. It may be the case that the cone of feasible directions is a strict subset of the linearizing cone. Okay, so let's see what we are. So cone of descent directions in Rn, such that this is the objective function itself and u is less than 0. Cone of descent directions, those are cone of descent directions means directions that if you move along them, you go to a new point at which the function f is strictly less than f of x tilde. Okay, so descent directions, cone of feasible directions. So here, cone of descent directions, the focus is on the objective function of the optimization problem. The cone of feasible directions, the focus now is the constraints, and it gives you the directions such that there exists t greater than 0 and x tilde plus tau d for is feasible for every tau between 0 and t. So these are the directions you move into. You remain inside the feasible set. And then there is the linearizing cone, which is defined in terms of the gradient vectors. And again, objectively speaking, if you follow the arguments on the previous page, the linearizing cone, what we can say objectively about it is that if we are basically we have a direction or a vector in the complement of the linearizing cone, which means that we have here not equal to 0 or greater than 0 in that case, then we are guaranteed to go outside the feasible set. Okay, so that's the linearizing cone. So the linearizing cone, its complement is a subset of the complement of the cone of feasible directions, and so the cone of feasible directions is a subset. Sometimes it's a proper subset of the linearizing cone. Okay. Now define this matrix. So we will define a matrix. So we have a matrix psi, okay, will be the gradients of the inequality, the functions involved in the inequality constraints that are active. So the functions involved in the active inequality constraints. We have P of them. The phi matrix, okay, is a matrix again. The columns are the gradients of the functions involved in the equality constraints, when we require that every g is equal to 0. Okay, so those are g1, and we have basically m of them. Okay, so what we'll do is that we will define a matrix minus psi, phi minus phi. Okay, so how many columns do we have? So we have b columns from here, m from here, m from here. So we have p plus 2m columns. And so this is a matrix. So we will actually apply the Farkas lemma, and our heroes now will, Farkas lemma from the previous lecture. You need two things. You need a matrix, you need a vector. And so the matrix will be this thing here, which definitely is not intuitive. I mean, what are we doing exactly? So we have this matrix, again, minus psi. So we are taking minus the gradient vectors of the active inequality, of the functions involved in the active inequality constraints. And we have phi and minus phi, where phi basically are the gradients of the functions involved in the equality constraints. So this will be our matrix. And then the Farkas lemma requires a vector. The vector will be the objective function, the gradient of the objective function itself. Okay, so what is the Farkas lemma? So let us have a reminder of what the Farkas lemma is. So basically we have a matrix, let's say big omega, and then we have a vector, let's say that it's beta. Then we have two alternatives. We can find a vector, we can find a non-negative vector, okay, such that, so big omega, we can find a vector, let's call it z, is equal to beta, and z is non-negative. So this is one alternative. Another alternative, there exists, let's say, another vector z bar, such that z bar transpose omega is greater than or equal to 0. So the inner product of this vector and each column in omega is non-negative, and z bar transpose beta, so the inner product and this vector is strictly negative. So Farkas lemma tells you, these two statements cannot be true simultaneously, and they cannot be false simultaneously. One of them is true and one is false. If you show that one is false, the other must be true. Okay? So this is the Farkas lemma. We will apply it now using this matrix and this vector here. Okay, so we will start now with the second alternative. So one alternative is that there is some direction D, such that the inner product with this vector, which is the gradient of the objective function, is strictly negative. What is the meaning of this? What is the meaning that there is a D with an inner product with the gradient vector of the objective function that is strictly negative? So D is living in what cone? D is in what cone? Its inner product with the gradient of the function at x tilde CDD, exactly, the cone of descent directions. If this is the first page on this lecture, basically that, if there is something that makes an inner product with the gradient that is negative, you can go along this direction with a sufficiently small step, and you will reach a point with a value of f that is smaller than f of x tilde. also, by the Farkas lemma, we are still in this alternative. Basically, what we have is that D transpose multiplied by all those guys should be greater than or equal to 0. So minus D transpose psi is greater than or equal to 0, minus D transpose phi is greater than or equal to 0, and plus D transpose phi is greater than or equal to 0. Now, if this is true, if something is greater than or equal to 0 and minus the thing is also greater than or equal to 0, it must be the case that D transpose phi is exactly equal to 0, which means that the D, if its inner product with any column of phi, and those are the gradients of the G functions, those are zeros. And you take this inequality, multiply both sides by -1, and you get that the inner product D and any, and the gradient of any of those functions involved in the active inequality constraints, those will be non-negative. What is the meaning of this? D is also in what cone? So the directions inner product with the gradients of the G functions 0, the gradients of the H functions less than or equal to 0, so long as we are talking about the active inequality constraints. That's exactly the definition of somebody living in the linearizing cone. So this alternative means that there is a vector in the cone of descent directions, and at the same time in the cone, in the linearizing cone. So this means that the intersection between these two cones is non-empty. There is an intersection between these two cones. So who cares? Well, the problem is this. The cone of feasible directions is a subset of the linearizing cones. Okay? So basically, we are afraid that this intersection means that there is an intersection between the cone of descent directions and the cone of feasible directions. Why is this problematic? What is the problem if there is a direction that is in the cone of descent directions and that is a feasible direction? What's the problem? What does this mean? So we have D. Suppose that D is a feasible direction and it's also in the cone of descent directions. So this means what? This may give you an indication that what is going on. I'm not talking here rigorously. I'm just giving you that there is a danger that X tilde is not optimal, right? It's not optimal because if at X tilde you can move in a direction that is feasible and that leads you to a point at which the function is lower in value, then X tilde itself is not the minimum. It is not the point at which the function is minimum, right? But so objectively speaking, this is what we have, that this intersection is non-empty. Can we actually make the judgment that X tilde is not optimal? Again, I will postpone talking about this. But for now, the optimality of X tilde, that's the reason I'm writing it like this. If there is an intersection between the cone of descent directions and the linearizing cone, perhaps X tilde is not optimal in the sense that perhaps it is not the point at which the function is minimum. But the Farkas lemma tells you that there is another alternative. So basically, it may be the case that this is false and there is another alternative. And so what will be the other alternative? So the other alternative will be the opposite of this one. So this one tells you that the intersection between the linearizing cone and the cone of descent directions is non-empty. So the other alternative will tell you that the intersection between the linearizing cone and the cone of descent directions is empty. And this is the KKT condition. Or actually, we can take this statement and from it we write not just one condition, but a number of conditions, the so-called KKT conditions. Okay? So the KKT conditions in their raw form and without making any further assumptions, we just want our functions to be C1. KKT conditions means that basically it's like sort of an abstract statement or a statement that is not so like it is not so clear what to make out of it, but that's what it means. The intersection between the linearizing cone and the cone of descent directions, this intersection is empty. Okay, but from the previous lecture we can actually write down this other alternative in a nice way, and so this will lead to the KKT conditions as you know it. I mean, actually, I'm sure that like most of you, even from homework 1, you know the Lagrangian and so on. So let's see actually how the expression for the Lagrangian is derived. It's basically just take this other alternative and apply it. So if the above is not true, then the other alternative is that there exists a vector D. D is non-negative element-wise, such that the matrix of the Farkas lemma multiplied by the vector, and I will basically write down this vector here in a block form. So basically I will divide this vector into mu and z1 and z2 stacked on one another like this. Remember that this matrix, it has B plus 2m columns. So there exists a non-negative vector such that the vector of the Farkas lemma, which is the gradient vector, is equal to the matrix multiplied by this vector here. Now, basically multiply. Okay, so from here we have delta f of x tilde is equal to minus epsilon mu, so this multiplied by that, plus phi z1 minus phi z2. Okay, and again mu greater than or equal to 0, z1 greater than or equal to 0, z2 greater than or equal to 0. That's the Farkas lemma. Now move those to the other side. Move those to the other side. So you get that the gradient vector plus epsilon mu plus phi multiplied by these two vectors, z2 minus z1, is equal to the O0 vector. Now z2 is a non-negative vector, z1 is a non-negative vector, but what happens when we subtract a non-negative vector from a non-negative vector? We can get anything, right? We can get anything, and so I will just write that phi is multiplied by lambda, and lambda now is not necessarily, so lambda here, not necessarily non-negative, again, two vectors, each one with non-negative components, but their difference can be negative, okay? So not necessarily non-negative. But the epsilon matrix, it's multiplied by something that must be non-negative. Okay. And so I will expand this because we know psi and we know phi. Okay, so I will write this plus psi mu. So here we have j from 1 to b mu lj, and then we have the gradient. So the columns of psi are basically the gradients of the h functions. So those are the guys involved in the active inequality constraints. Okay, njx tilde. And then we have the other guys. We have m of them, lambda k, gk of x tilde. Okay. Again, there is this point that basically we worked with the h functions involved in the active inequality constraints, the constraints that are satisfied with the strict equality. But actually, you can take this sum here and write it as a sum over all inequality constraints. Okay, so what we will do is the following. We will write this sum as a sum involving all inequality constraints, and we will assume that, but you will say, okay, so what are those coefficients if you use the gradient vectors of the h functions involved in inactive inequality constraints? Well, the corresponding mu's, we will take them to be equal to 0. Okay, so because the issue is that before solving an optimization problem, you don't know which inequality constraints at the optimal solution will be satisfied with a strict equality or strict inequality, right? You don't know. So better basically to have an expression that involves all the constraints, and then we will remind ourselves that if our inequality constraints are inactive, which means that they are satisfied with a strict inequality, the corresponding mu will be exactly equal to 0. Okay, so this is what we get for the Farkas. So so basically the KKT conditions are this statement that the linearizing cone and basically the cone of descent directions, they have an empty intersection. And we can write down this mathematically as this expression here involving the gradient of the objective function and the functions involved in the constraints of our optimization problems. Now, our expression also involves the mu's and the lambdas, and so those are called the Lagrange multipliers, or basically the dual variables. So these guys are called the dual variables, or Lagrange multipliers. We will have to live with them, and they will play a very important role in obtaining the optimal solution using the KKT conditions. Any questions? Okay. So here are the KKT conditions. You have basically a general constrained optimization problem. You start by something called the Lagrangian. Okay? So if you look at the Lagrangian, it looks like what I had on the previous page, but without the gradient vector. Okay? So the Lagrangian will be basically, it depends on x. Sometimes you need to emphasize that it depends on the x, the u's, and the lambdas. So it is the objective function plus a weighted combination of the inequality constraint functions and those G functions involved in the equality constraints. Now, the KKT conditions become those conditions. Stationarity. It means that the gradient of this Lagrangian is equal to the all zero vector. This is exactly what we had on the previous page. So basically you want the gradient of f plus the summation mu, the gradient of h plus summation lambda, the gradient of g, to give you the all zero vector. Okay? Now, to say that the KKT conditions are satisfied at some x tilde, we want x tilde to be a feasible point. We are hunting for the solution to the optimization problem. So we need x tilde when it's basically used with the h functions to give you a result that is less than or equal to 0, and with the g function 0, we want primal feasibility. We want basically the constraints of the original optimization problem must be satisfied. Otherwise, x tilde is not feasible and we are not even interested in it. Then when we introduced those new guys, it turns out that those guys must be non-negative. And so we have, those are called the dual feasibility conditions. We need those guys to be non-negative. Okay? So those are the KKT conditions, okay? The KKT conditions. And again, like in an abstract form, they mean that CL of x tilde intersection CDD at x tilde is the empty set. But we have also, complementary slackness, which is very useful. And for those of you who attended the lecture in the morning, actually we used complementary slackness to solve the power control or power adaptation problem in a wireless system. Okay, so what is complementary slackness? It is not something new, by the way. It is not something new. We are basically rewriting what happened on the previous page. We are not inventing anything new, but we are basically trying to write everything like in a structured way that will help us use the KKT conditions to solve optimization problems. Okay? So here is the complementary slackness conditions. For every term that you have here, mu j multiplied by hj of x tilde must be 0, which means that one of those two terms must be 0. It cannot be the case that that both terms are non-zero. Why is this the case? Right? So let's remind ourselves of what happened on the previous page. So basically, if h of j is an inactive constraint, inactive inequality constraint, it means what? It means that h of j x tilde is strictly negative. And remember, those guys were not in our initial expression. We said we introduced them, coupled with mu j that is 0. Right? So basically, if you remember the psi matrix from the previous slide, it involved basically the h functions, that are that were not the h functions that were active, satisfied with equality. And then we said, oh, okay, so let's write the sum using everything. And we understand that basically the mu's that are multiplied by hj's, that those the mu's that are multiplied by hj's should be 0. Okay. So if we come here, it means that if the h function is strictly negative, you must have the associated mu to be 0. Okay. And now, if mu is greater than 0, okay, if mu is strictly positive, then again from our previous analysis, it must be the case that we are talking about one of those inequality constraints, that are active, that are satisfied with strict equality. So in both cases, the product must be 0. Again, we have two cases. In one case, the inequality constraint is inactive. This function is strictly negative, and then to include it in the Lagrangian, we should have mu to be 0. And in the other case, mu is strictly positive, and so that's basically it means that we are talking about an inequality constraint that is active, which means that it is satisfied with strict equality, which means that it is 0. In both cases, the product is 0. And so this is very useful. Again, complementary slackness can tell you exactly how your solution to a constraint optimization problem should proceed. So the KKT conditions, okay, so this is their main form, but it's not so insightful, not so useful in practice. If you want to solve optimization problems, those are the KKT conditions. And, basically they are equivalent. But again, we are writing them in such a way that is useful if you really want to use the KKT conditions for solving an optimization problem. Okay. Let's use the KKT conditions to solve this problem. x1 plus x2 we want to maximize subject to those constraints. First order of business is basically to put our optimization problems, to put our objective and our constraints in the standard form. So the standard form, we minimize the function, and so it's easy. If you want to maximize a function, this is equivalent to minimizing the negative of the function. And the standard form for the inequality constraints are less than or equal to 0, not a problem. Multiply both those inequalities by, okay, so we can write this one as minus x1 less than or equal to 0, this one as minus x2 less than or equal to 0, and this one we can write it, so we want our equality constraints to be a function equal to 0, not a problem. I can write down this constraint as x1, x2 minus 16, so this will be my function of x1 and x2 equal 0, not a problem. Okay, so we need like those tiny tricks basically to take like a general optimization problem and make it basically conform to the standard form. And so our problem now becomes minimize minus x1 minus x2 subject to basically those constraints. Now every constraint is written in the standard form. Write down the Lagrangian. Okay, so the Lagrangian will be, so here is the objective function. Okay, so here is the objective function. We are minimizing minus x1 minus x2, and then we have those constraints. Okay, so for each constraint we have a dual variable or Lagrange multiplier. Okay, and those guys must be non-negative. So we have plus mu1 and then this function minus x1 plus mu2 and then this function which is x2, and those should be non-negative. And also we have an equality constraint, so we have a Lagrange multiplier here that is multiplied by x1 x2 minus 16. So this will be our Lagrangian. Next lecture we will basically try to see what the KKT conditions do, and we will discover something like sort of bad news, that the KKT conditions in the raw form are neither sufficient nor necessary for optimality. So a point satisfying the KKT conditions may not be optimal, and a point not satisfying the KKT conditions may actually be optimal. So the KKT conditions in the general case, they are neither sufficient nor necessary for optimality.